So we begin with the Sun. Now, in the we have a vast stellar system, okay, to which we belong, and this stellar system, like our galaxy, is Milky Way. This is consisting of about 10 to the power 11 stars, an estimate. It's a very fairly accurate, if I might say. Now here the Sun is just a mediocre member. So our Sun is a mediocre member. But it is the most important star from our point of view. Why is that? Because it is the most near to us, and we can study it in every possible aspect. So the Earth and the major and minor planets, comets, and everything, these comets, asteroids, is in the control of Sun. Okay. Directly and of course indirectly, because everything attracts everything else. So the motion of every member of the solar system, big or small, has got a direct influence by the Sun. Now the Sun is the only star which shows a disk. Right. And these different parts of these disks can be studied. We can do physical studies. So now it's in most of the cases, unlike the other stars that we see in our night sky, is like a point source. So this is a disk. From the optical perspective, this is a disk, and the rest of the stars are point sources. So this is an important distinction, the optical distinction. It is the source of almost all the energy that we use. So there are like astronomical considerations, lots of astronomical considerations, which we will omit, because this is what we are studying is the astrophysics. So we won't mention anything related to those astronomical detailings. So we will come directly to the physics part of it. Okay. So we now fairly know fairly accurately know the values of pressure, density, temperature, all the way from the surface to the center of the Sun. Okay. So what are the things that we know? We know the pressure at every point of the Sun within it, the density, pressure, density, and temperature. These are the elements of investigation. The radiant energy. So what is happening inside is the thermonuclear transmutation of hydrogen into helium. Okay, these are the physical, the physical terminologies. Okay. So thermonuclear transmutation of hydrogen into helium, and various isotopes of it. And due to this, we get a radiant energy, and which is the source of all the energy that we use. Okay. So what is the central temperature? Again, this is astronomical information. Central temperature is about 16 million Kelvin. So as we say that we have a fairly accurate model of the interior and atmospheric structure of the sun. So we construct models for the distant average stars based on these models, and we can thus understand the physical nature of these stars. We also do spectrum analysis of the other stars to obtain information about the other things regarding the stars. But we can very much use the model that we build using the information that we gather from sun. Now the main body of the solar interior cannot be directly observed. Main body of solar interior cannot be directly observed. So how do we gain the knowledge? So we extend the knowledge to the interior by applying laws of physics. So we gain these things by applying the laws of physics governing the equilibrium of radiating gaseous sphere. Okay. This we do in combination with the observed results from the upper layers. So basically, if you see the different layers like this interior, we cannot directly observe. We observe some phenomena here in these upper layers, and we extrapolate using the laws of physics. So the problems of the overall equilibrium structure, thermonuclear energy generation at the core, mechanisms for transporting energy, how the energy gets transported from interior to outside, and everything, this we will discuss later, but not in this lecture. So the interaction of the outgoing radiation with the relatively tenuous atmosphere, this we consider later on as well, because these are the things that will require the knowledge that we gather in this particular lecture. So here, now today what we will discuss is that only the observable aspects of the sun and some of the physical theories which are applied to find the satisfactory interpretation of these observed results. So basically what we study are the observable aspects of the sun. So what are these observable aspects? Like say sunspots. Okay. So sunspots and faculae in the photosphere. There are lots of terms for this: the sunspots, faculae, the spicules, and plages. Okay, so this we will write down the terms: faculae, spicules, and the plages. Then there is the chromosphere, the prominences. Then the prominences. Flare. Now all these things are different. Okay? The streamers in the corona. So these are the chromosphere features. These are the coronal features. Then we have the solar wind. Then we have this sporadic radio bursts. These are from the outside, the outer atmosphere. Okay, so if we want to draw how the sun looks, okay, so this is the core. From core, the outside surface is about 695,000 kilometers. Okay, the middle of the outside surface. So we will draw like this. So here we will see some kind of granules. Okay. We will see the spicules. This is the radiative zone. use a different pen. This is the radiative zone. This is the nuclear reaction happens here. Okay. This is what is called the photosphere. This area is the photosphere. And here is the chromosphere. This is where the corona lies. So this is the coronal streamers. The coronal streamers goes like this, prominences and bursts. Okay. Everything happens in this area. In the entire chromosphere there is a photosphere and there is a reversing layer. So now it's generally believed that the most of the solar phenomena and the physical explanations we understand very, very clearly, very well understand. Even with some recent discoveries about the sun, it is confirmed. So sun is pulsating with a period of nearly 2 hours and 40 minutes. So it is pulsating. And the pulsating period is 2 hours 40 minutes. What is the amplitude of this pulsation? Amplitude is very, very small. So the amplitude is about 10 kilometers. What do we mean by pulsating? Pulsating means the sun is increasing in radius and then decreasing in radius. That's what pulsating means. And the difference in the radius is about 10 kilometers, which is very, very small. The average radial velocity, like the velocity with which this radius increases or decreases, is about 2 to 4.5 meter per second. So we call this the average radial velocity. We call this the average radial velocity. It is 2 to 4.5 meter per second. So now we do various different types of analysis, okay, and we analyze various consequences. So this thing that I've been telling you is quite a recent discovery. So, but this pulsation has a very far-reaching consequences of our present understanding of the physical processes of the sun. So basically, that the solar energy that is getting generated, okay, does not occur by the hitherto well-known proton-proton. So basically what we have been talking about is that the proton-proton interactions, proton-proton reactions at the core is the sole generator of the energy, but which and this idea is being challenged now. Okay. So but it is definitely a theory because it is supported by various different independent experiments. Okay. So the proton-proton reactions are operative in the core area. Okay. So this is the area where the proton-proton interactions are operative. Then a certain amount of neutrino flask should emerge, and the reasonable amount should be capable of being detected by other set of experiments. So these recent discoveries, they indicate that the time may not be very remote and may be very, very near, that when our present understanding of the solar physics may have to be drastically revised. Okay, so this pulsation that we discussed is a very recent still, and in our discussion, the things that we will be discussing, we may not focus on these pulsations in great detail, because this is the thing that will change the physics, and that change is yet to come. So we will come to the photosphere, the limb darkening process. So this is the photosphere. And what we will see is the limb darkening. So the atmosphere of the sun, as we have mentioned, and basically the astronomical things that we will not discuss, like the structure of the sun, the layers, and various different things. So we will just hint them. So the atmosphere of sun is composed of layers and hot gases. These layers are not very sharply defined. Okay. So although we draw spheres and circles, these are not like that, not very sharply defined. So each one of these is separated by transition zones. So there are transition zones that are several kilometers long, or rather thick, and these layers, they greatly differ from each other in terms of their physical characteristics. Okay. So the surface, the solar surface that we see when we look up the sun, is the visible solar surface. So these layers are known as the photosphere, the surface that we see when we look at the sun. So that is what is the photosphere. The chromosphere and the corona, these are the last like the last one merging into the interplanetary space. So just after photosphere, so basically the sun's layer, okay, the top layer is the photosphere, just above that, when it is merging to the interplanetary space, that is what is chromosphere and the corona. Okay, so again, if we look at the sun's image, so this is the photosphere, that the surface that we look at, and this is the area that merges with this, with the interplanetary space. This is where the chromosphere and the corona. So all the chromosphere related things, the things that we talked about, like the facules, the spicules, the plages, and things like that. Then the coronal features that we talked about, it's the prominences, flares and streamers and things like that, that all happen in these areas where the layers merges with the interplanetary space.
Thomas.
So the temperature that is attained at the transition layer between the photosphere and the chromosphere, this temperature increases very rapidly both ways from this layer, which is often known as the base of the chromosphere. So this is the base of the chromosphere. So minimum temperature is 4200 Kelvin. The temperature at the base of the photosphere is more. Temperature here, so this is the photosphere. Temperature here is about 5800 Kelvin, and this is where our view is obstructed. Okay, so if we really plot these temperatures, what we will see the height in kilometer. Okay, and if we plot the temperature in the y-axis, we will see somewhere, say for example 0 is the this is, say for example, this is where the photosphere is, and then onwards is chromosphere, and here is the photosphere. We will see that this here, the temperature is lowest, and the temperature then rises like this, and the temperature rises like this. So basically this is about roughly 6300. This is about 45, about 4000, and then the temperature rises in the chromosphere. So this is what is known as the temperature distribution near the photosphere chromosphere boundary. Now the visible disk that we talked about. The visible disk is the solar surface. So as we say that we cannot look beyond this photosphere. So this is the visible disk, is the base of the photosphere. The innermost layer of the solar atmosphere to which our eyes can penetrate, beyond which is not observable. So now the thickness of the entire photospheric layer, this is it is completely transparent to perfectly opaque layers of gas that is quite small, okay, only of the order of 200 to 300. So why we cannot see inside is because of that teeny layer, okay, which is about 200 to 300 kilometers thick. This dense layer of gas. Now what we see from the sun is known as the continuous absorption spectra. Is the continuous absorption spectra, and this is when we see that this is predominantly being contributed by the H- ions. Okay. So H- essentially means protons. So we know that this photosphere is almost entirely consisting of protons. In most of the Fraunhofer lines, so in this absorption spectra we see that the Fraunhofer lines that we see in the spectra they do originate in this layer. So most of it originate in photosphere. So later on, when we study the hydrogen atom, proton, using quantum mechanics to work it with the quantum computer, we will see that there's a specific kind of energy systems that we can study here using the photospheres of using the protons in the photosphere of sun. Okay, so this is a very important thing, that the most of the lines originate in the photosphere. This is something that we need to remember. Okay, so this is a new information, of course, because previously it was believed that these lines form in the lower part of the chromosphere, which has been given the name reversing layer, meaning that the most of the reversed lines, the absorption lines, reversed lines means the absorption lines, of the solar spectrum originate in this layer, but the current observation, experimental studies had revealed that most of the solar absorption lines originate in the photosphere. The weaker lines in the lower photosphere, the stronger lines in the upper photosphere. Now, in these Fraunhofer lines, there are some very, very strong lines. So basically weaker lines originate in the lower photosphere, and the stronger lines originate in upper photosphere. But there are some very strong lines. Very strong lines. These are the lines that we studied earlier in the absorption spectra and emission spectra, called Balmer lines. These are known as the Balmer lines of hydrogen. And there are some lines called the K lines of Ca. These has their origin primarily in the lower chromosphere. So these happens in the lower chromosphere. So as we say that we know the pressure and density in the photosphere, these are much, much lower in comparison to those of the terrestrial atmosphere at sea level. Like the pressure is about 10 to the power minus 2 of the pressure in terrestrial sea level, and density is about of the order of 10 to the power minus 3 in the terrestrial sea level. So this is pressure and this is density. Okay, what is the standard pressure at sea level? The standard pressure at sea level is also a figure that we should remember. It's about 2.7, 2.688 in fact, into 10 to the power 19 centimeter to the power minus 3. Now this depth of the photosphere through which now we can see the photosphere through this, we have already stated. So we now see on the disk, this part that we are observing, and the opacity of the photosphere also that we talked about. The deeper and hotter photospheric layers are observed when we look at the sun's disk near the center. So as we look near about these things, we can see the deeper and the hotter photospheric layers. When we see the disk near the limb, near this region, the limb region, what happens is that we basically view our view basically penetrates through the cooler superficial layer of the photosphere. How does that happen? So basically, when you look at these sun's disks, so suppose this area, I expand this area in this way. So when we look through these areas, what we are doing is we are viewing through these areas. Okay. So this basically is the photosphere layer. Is basically the photosphere. So so evidently in these areas our view penetrates much more than these areas, because these are the areas where when we look through this area directly, this area at the base of which this region, this opaque region occurs. So you cannot see beyond that. But through these areas, these are the near the limb, we can see very deep. Okay. So that is why. So we go through a much deeper view in these areas. So that is why the well-known limb darkening effect occurs. Okay, so this is why it's called the limb darkening. So this is much brighter part, and this is as we go more towards the limb, it becomes darker and darker. So this is what is known as the limb darkening. Okay. So what happens is light from the near edge of the disk comes from the upper, cooler and the more tenuous layer of the photosphere than that from near the center. Okay. So if you really see like that, and this is the sun's disk, and this is where our detector is, and this is something that we see. Okay. This is the photosphere that we see. This is the photosphere, and this is the tangential view that we see. So you see that this goes through the photosphere. It doesn't go into the sun at all. Okay. Similarly, it goes through the photosphere chromosphere area. So these are upper cooler layers, and these are hot layers. Okay. Since this is cooler layers, that is why the limb darkening effect occurs. Okay, we see the limb of the sun, of the solar disk, getting redder and dimmer as compared to the bright and the hot central part. So this is much redder and cooler. So the brightness of the solar disk decreases as we go from center to, so this is center and this is towards the edges. The brightness decreases. So if we plot the brightness, so this decreases. So that means this is a temperature gradient that exists between the layers. Okay. And as we show here, see that the temperature gradient, the temperature increases again. Okay. When we come into the photosphere, into the chromosphere area. So it rises very rapidly, see. The gas density in these upper layers is very, very low. Okay, so what happens when the density is very low? When the density is very low, it is capable of absorbing or emitting very, very small amount of radiation. Density low means less number of protons, and they absorb less, they emit less. Okay. The opacity is also very low because of the same reason. The density is low. These layers are almost transparent compared to the photosphere. So this is why the disk appears to terminate abruptly at the end of the photosphere. Because these areas have very little density. So in our next lecture we'll consider the granulation and the faculae, the spicules and these flages, filaments and these things. And then we'll come to the solar corona.